We talked about one form of error whenever you find the sum of a polynomial. It was called the alternating series error, and we'll go back and we'll do some more problems with that later. But we got to talk about another form of the remainder. This one is called Lagrange form of the remainder. And most of the time, this remainder is used when you estimate like e to the x or sine x or cosine of x with a polynomial, and it's the error that determines how far off we are from the original equation. So first, let me write down what the formula is. Rn stands for the remainder. So this is saying the remainder is equal to the original function minus the approximation. I think that makes sense. That if we're trying to find the remainder, that we take the original minus the approximation. The approximation is a Taylor or a Maclaurin polynomial. And then your formula is this. And I'll explain what that means because the symbols are kind of strange. Alright, it says f to the n plus 1 of z. That means the next derivative. If it asked me to find the third degree polynomial, well, this would mean, that right there would mean the fourth derivative. So whatever polynomial I'm trying to find, it's the next derivative. That's what that says up there. It says the next derivative at z. Okay, z is another thing that we need to talk about. Z is the number that would give us the biggest value, and I'll show you that when we do some problems. And then you'll recognize the n plus 1 factorial. That's like if you're doing a Taylor or Maclaurin polynomial, that's what's next. It's the term that's next. Then you do x minus c. C is where you're rotating around, or like where the center is, and then to the n plus 1. So you'll recognize most of it, like this part and this part, as the polynomial. It's just that f to the n plus 1 looks strange, but it means the next derivative and at z. So z is the thing that normally we would need to find, and I'll show you that as we work out some problems. So first of all, the problem example says find the accuracy of the third degree polynomial, Maclaurin polynomial, for sine of 0.1. So what we have to do first is we have to figure out what P3 of x is. Now, if you use what we did yesterday in the video from yesterday, I hope that you will know that you start with sine of x, you find the derivative of sine, and you do it till you get to the third place, and then you write out the polynomial. I'm going to go ahead and tell you that this equals x minus x to the third over 6. I hope that that's something that you understand and you can do that. If not, I can show you that later, so be sure to ask. But that's what the polynomial would be if I go to the third place, because it says p of 3 of x. Now it says using p3 of x, we want to estimate sine of 0.1. So what that means is that we want to plug 0.1 into x in that equation. If you do that, you get 0.09983. And I just wrote several decimal places just so we can compare later on. So now what we really want to find is we want to find the Lagrange form of the remainder. That means R3 of x. Since P3 of x, or the third degree polynomial, is the one we looked at, that means that we're finding the remainder up to the third degree. But the formula, because the third degree is what we started with, think about this formula up here, it's the next one. So our formula is the fourth derivative of z, and then x to the fourth, because we know it's Maclaurin, so we know it's going around 0 for the c, over the 4 factorial. So here's our formula. That's our formula that we're going to use. So, we want to figure out what the fourth derivative is, and hopefully if you understand where the P3 of x comes from, you could do those derivatives, and hopefully you'll realize that the fourth derivative is sine of z. So in the interval, it's really, really important to think about, but sine of z is always between 0 and 1. Anytime that you have cosine or sine of something, I know that cosine and sine will always be between 0 and 1, which means the biggest value of z that I could come up with is wherever sine of z would be 1. So what that means is when I find the derivative in my formula, that 1 is going to go right there for the fourth derivative of z, because the fourth derivative of z is supposed to be the biggest value of the derivative at that place. And sometimes it's not going to be quite as easy as that, but if you have sine and cosine, it's just going to be a 1, and so you would just put a 1 in there. So what we find out, if we're trying to find the remainder, is that you have 1 for the fourth derivative of z times x to the fourth over 4 factorial. Now we're estimating this at 0.1, so we would plug 0.1 in for x to the fourth. So x equals 0.1. So that means that we have 0.1 to the fourth over 4 factorial. And we would get 4.166 times 10 to the negative 6. That's our error. That's how much we would be off if we estimate sine of 0.1 as using the third degree polynomial, or we get that value. So if they ask for the error, that right there would be the error. If they ask for an interval, what you do is you take what the value estimate was that we got way up there, and we say that sine of 0.1 is between that value, and then we add the remainder to what we estimated it to be. So this value I'm getting ready to write down is 0.09983 plus 4.166 times 10 to the negative 6. You would get 0.0998375. And then it keeps going. But we would say that sine of 0.1 is between there. You could put sine of 0.1 in the calculator and you'll find out that it is between there. Most of the time, it's going to ask for the remainder. Most of the time, it won't ask for the interval, but I'm showing the interval just in case. All right. Example 2 says to find the accuracy of the fourth Maclaurin polynomial for e to the negative 0.1. So what that's telling me is that f of x is e to the x, and the value that we're using that we plug in, or that we're estimating, is negative 0.1. Now it says the fourth Maclaurin polynomial, so that means that my remainder is going to be f to the fifth of z over 5 factorial times x to the fifth. It's absolute value because when we plug in that x, we're just going to plug in the positive values. Alright, so what we would do first is we would need to figure out what the fifth derivative of e to the x is. And I think that you can see that if f of x is e to the x, and we find the first derivative, and we keep going, since it's e to the x, all of them are going to be e to the x. So I know that the fifth derivative is e to the x. And what I need to figure out is what the biggest value of e to the x is. And with sine and cosine, I know that the biggest value is always 1, unless there's a number in front of sine and cosine. But with e to the x, I sort of need to think about the graph a little bit. Alright, here's the graph of e to the x. And because negative 0.1 is where I'm estimating it, then I want to think of an interval where negative 0.1 would be, and I use integers. So think of it between maybe negative 1 and 0, because I know negative 0.1 would be in between there. Is e to the x bigger at negative 1, or is e to the x bigger at 0? Well, it's bigger at 0, obviously. So what I'm going to put in for f to the fifth of z is e to the 0, because e to the 0 is bigger than e to the negative 1. So for my formula, I'm going to put e to the 0 up there for the fifth derivative at z, because 0 would be biggest. Leave our 5 factorial. We're estimating negative 0.1, so we're going to plug that in for x. It's an absolute value, and raise it to the fifth. And you would get 8.333 times 10 to the negative 8. And that would be our error. It's the accuracy. It's the Lagrange form of the remainder. Okay, example 3. It says that we have a function f of x equals cosine of 2x plus pi over 6. And p of x is the third degree polynomial. We want to use the Lagrange error bound, Lagrange form of the remainder, however you wanted to say that, to show this. Okay? Maybe you don't know what that last thing means. That's okay. But I do know that we're doing third degree Taylor. And so I need to think about, if I'm doing Lagrange, I need to think about the formula. Since it's third degree, it would be the fourth derivative of z over 4 factorial times, it says Taylor here. So the Taylor polynomial would be, oh, and it says around x equals 0. So it's still just a x in there, x minus 0. And then it would be to the fourth. If it said at x equals 1, then here I would put x minus 1 to the fourth. But anyway. So what that means that I need to find, even though I'm not sure about that last part of it, let's go ahead and do this, and then we'll figure out how that's used. But I do need to find the fourth derivative. So I'm going to go ahead and show you how to get the derivative, just because I think it's important for you to see the derivative. I'm going to go ahead and write them down, and then you can check them. Okay, there's all the derivatives. You have to remember that the derivative of cosine is negative sine. You also have to remember when you do the derivative to multiply by the derivative of the inside, which is 2. So here's the fourth derivative, and I needed the fourth derivative because that's on top. The first part that I need to figure out is, what's the biggest value of the function of the fourth derivative? Now, what I know is that if I'm just looking at the cosine part, I know that the biggest value of cosine of something is always 1. But I'm multiplying it by 16. 16 is the amplitude, and so if you think about the amplitude with cosine, it's not anymore, it's not but like negative 1 to 1, now it's negative 16 to 16, because that's what that amplitude is. So the biggest value of the fourth derivative at z is going to be a 16 on top. And then 4 factorial, and then something raised to the fourth. Alright, I think I'm ready now to tell you what this is. If you look back at what I told you originally that the Lagrange form of the remainder represented, I told you that the remainder was the original minus the approximation. Well, that's what this is saying, the original minus the approximation. And we're trying to prove that the original minus the approximation is less than 1 over 100. That means whatever I get here is supposed to be less than 1 over 100. Hopefully it will be. Now, because I put a 1/3 in parentheses, what they're telling me is that 1/3 is the place that I'm approximating this particular remainder at. So 1/3 will be the x value that I use. We're going to put this in the calculator, and you would find out that you get 0.008. We were trying to prove that it was less than 0.001, because 1 over 100 is 0.001. I think I'm telling you too many zeros. It's 0.01, and 0.008 is less, so we've proved what we needed to find. So we had to find the remainder after finding the fourth derivative and thinking about the biggest value. And then we had to find that the value that we get was less than 1 over 100, which is 0.01. Okay, example 4. So here's what we know. We know that the third degree polynomial around x equals negative 2 is this function. So they're giving me what p of x is. They're also telling me that the fourth derivative satisfies this inequality. And we're trying to find the error approximation for f of negative 0.16. Okay, so if I'm trying to find the Lagrange error form, I know that I started with the third degree polynomial. And so that means that I'm going to need the fourth derivative of z over 4 factorial times x minus 2 to the fourth. X minus negative 2, I'm sorry. So that should be x plus 2. Since it was about x equals negative 2. Since it was not around 0. That's why that's in parentheses there. Alright, when they tell me that f to the fourth of z is less than or equal to 25, what they're telling me is that the maximum value of the fourth derivative is 25. So what they've just told me is that 25 goes on top. They're telling me that 25 is the biggest value of the fourth derivative. 25 goes on top, 4 factorial. Our x value that we're using is negative 0.16. You would take the absolute value of that, but it will be positive, so that's the reason it works out that way. Let's plug that in the calculator. And I get 0.026 repeating. So this particular problem, the error would be 0.026. So here's another example. I know it's not on your sheet, but I need to talk about this just for a second. So, similar kind of problem as the others. We're talking about the second degree polynomial. We're talking about e to the x around x equals 0, and we want to estimate x equals 0.3. So, second degree polynomial, that means that if I'm finding the error, that I need to find the third derivative of z over 3 factorial times x to the third. Alright. The f to the 3 or third factorial of z. Alright. It's around x equals 0 and it's at x equals 0.3. Okay, think about e to the x again. E to the x looks like that. Here is 0. I know 0.3 is to the right of it. So again, I'm wanting to pick an interval. When we did that last problem and we did it from negative 1 to 0, that was okay. And we just chose 0 because it was the biggest. Well, here, you can go all the way to 1 if you want to, or to get more exact, we can just go to the 0.3, and we can say that the third derivative of z is the biggest at e to the 0.3. Since I know that I'm estimating at 0.3, I can put e to the 0.3 if I want to. If I wanted to put e to the 1, I could, but I might not get it as close as I wanted it to. So on a problem like this, I know that the third derivative would be e to the x, since we're talking about e to the x. And I know that on e to the x, the closer I go to the right, the bigger the values are going to be. So since I'm going around 0 and it's at 0.3, e to the 0.3 is the biggest value, over 3 factorial times 0.3 to the third, and we get 0.006. So here's two problems that I want you to try. On the first one, it's asking for several things. First, it says find the fourth degree polynomial. So that's like work out the whole problem, figure out what the fourth degree approximation would be. Estimate cosine of 0.1, that means plug in the 0.1 for x. Find the error, that means do this new thing. And since it's the fourth degree, you would use the fifth derivative. Number 2. It's a different kind of problem, but the interesting thing is that they've given you the derivatives, and they've also told me that the biggest derivative at 4 is 20. And so we want to figure out the third degree polynomial, and we want to figure out if the error bound is really less than 10. And so you'll use your formula to try to figure out what the error would be for that particular problem.